Okay, good morning. I think we're ready to begin. I'm Rosalind Picard. I'm the advisor to the doctoral thesis that's being defended this morning. And it's my pleasure to also welcome the two other members of the committee, Whitman Richards from MIT and Yannis Alamonis from the University of Maryland. And I just want to say that it's been a pleasure working with Nick. I've known him since he took my pattern recognition class a long time ago, and he's always been an exemplary learner and curious mind. So I think you'll enjoy his new interpretation of GSMs today. So I'm not going to say much more because we're already running late, but a little bit about procedure. Nicholas is going to talk for a little less than an hour. Then we have open question and answer time. And after that, any MIT faculty are invited to come down and have additional Q&A with Nick. And then we'll chase them away, and just the committee will meet privately, and we'll come to some sort of decision about whether or not he's passed his defense. And if he passes the defense, then there will be a little celebration upstairs in the fourth floor afterwards, and people are invited to that as well. Okay, so we'll go ahead and get started.
Thank you very much for the introduction, Rose. So my name is Nikolaos Mavridis. I'm a PhD candidate at the Media Laboratory here at MIT. And first of all, I would like to welcome all of you to my thesis defense, most honorable committee members and MIT faculty and all of the guests over here. The title of my thesis defense is Grounded Situation Models for Situated Conversational Assistants. And I guess that these terms are going to become much clearer as we progress through the presentation. So when I first came here, I was actually given access to this robot whose name is Ripley, and I was given the task of trying to turn it into a conversational helping hand. This robot has 7 degrees of freedom. It has a vision system, 2 cameras attached to its endpoints. It has a gripper through which it can manipulate objects, and it can also it has the ability for speech recognition and speech synthesis too. And a lot of what you're going to see today basically started from this robot as a platform. I would like to first start with acknowledgements. I would like to thank very deeply my thesis committee, Rose, Whitman, and Yannis, for making this possible. I would also like to thank very deeply Deb Roy, with whom I cooperated for quite a long time throughout my years at MIT, and who is actually one of my main collaborators in all the things that I'm going to present today, and from which I have been inspired in many and multiple ways, and with which we have so many papers together, too. Apart from that, I would like to give a deep thanks to Kai-Yu Xiao, who was the second person that was working on the platform of Ripley the robot for quite a while, and who is also responsible for the motor control system of the robot that you're going to see, plus a couple of other components, and who was also always extremely helpful whenever we had something with a robot. We collaborated in order to get things working. Apart from that, a warm thanks goes to all of my ex-Europes and all of the cognitive machines group and the affective computing group. So the central theme of this thesis is pretty simple to state. So the question is, how can we build what I call situated conversational assistants, which is going to be defined very soon, around the notion of grounded situation models, which are model representations of current, past, or imagined situations that can furthermore be fed both by the senses and by language. So the vision of this thesis is simple to state, and it was stated already. It is cooperative, situated conversational assistants. The contributions of the thesis consist of a proposal which is called the grounded situation model proposal, which is not only a theoretical proposal. There is also quite a specific and practical part to it. There is a code base that has been developed, plus an implemented system around this code base. This proposal consists of 7 parts. The first is a theoretical motivation and requirements. Then there is an explicit computational model for the grounded situation models, specified down to a level of pseudocode and also with existing code to support it. There is a modular implementation architecture for building systems around GSMs, an implemented system, which is Ripley the robot, evaluations, quantitative and qualitative, as well as a methodology for evaluating such complex systems, which is not a very straightforward task. A discussion of future extensions, this is pretty much like a 5 to 10 year research plan that takes significant leverage from what already exists over there. So we're not just talking about future extensions that would not reuse what we have, but I'm talking about things that would heavily reuse whatever is there. And a long discussion, but I hope quite interesting, of the relationship of the GSM proposal to other prominent theories in artificial intelligence, cognitive science, and semantics. So let me start with quite a simple way of introducing things. Let me show you what were the abilities of Ripley the robot back at the time when I started being here, and how these were enhanced after the introduction of GSMs and the implementation of GSMs on Ripley. So during the first semesters that I was here, the capabilities of Ripley were quite limited. He could only basically service simple motor command requests, and he could only, one could only refer to objects that were currently visible for Ripley. So if something came out of sight, it didn't exist anymore. People could not ask questions. People could not refer to the past. Users could not ask Ripley to imagine things, and so on.
Look at the table. Find the beanbag.
Which one?
The green one. Find the beanbag.
Which one?
The green one.
Which green one?
The top one.
So you see this is a vision system of Ripley. These are the currently visible objects, and they're the only ones that can be referred
Find the
to.
blue beanbag.
So there is no notion of things existing that are out of sight. There is no episodic memory. There is no possibility to actually give information about the state of the situation through language. You cannot tell to Ripley that there is something behind him and expect him to get sensor expectations for it. And there is no sort of keeping of multiple gradations of certainty about situations or multiple alternatives. So this is pretty much where we were something like 1 year ago from now. And here you're going to see the new capabilities that were added by the use of the grounded situation model. We're going to visit this video again after I describe with more precise terms what exactly is going on. So just get a rough idea from this first viewing. Where is the red one?
At the top.
Look at the center. So simple questions about the current state of the situation.
Okay.
Now notice that the object has come out of view, but it still exists within the situation model, and multiple gradations of certainty about its position are being entertained. This is what the camera view is. Where is the red one?
Most probably at the top.
What color are the objects?
One is red and the other is green.
Imagine a blue object on the left.
Okay.
So this is a crucial part. Here an informed statement was given, something like imagine a blue object on the left, or there is a blue object on the left. So there's no evidence about this object through vision, for example, or proprioception, but there is evidence through language. And a token was instantiated within the situation model, which contains all of the level of specificity that was given by the statement. So we know it is somewhere on the left. We don't know anything about the size of the object. But notice that we can still both refer to it and answer questions about it. And later, when we actually go and see the object, we can update the information that we have. Where is the blue one?
Most probably at the left.
How big is the blue one?
I have no idea.
Look at the left.
Okay.
Now notice that we actually saw the object that we had a sensor expectation for, and we're much more certain about its position, and we're slowly converging to the right size too.
Okay.
How big is the blue one?
Small.
And we know that it's small now. We had no idea. How big was the blue one when your head started moving? So simple references not only to objects of description, but also to events. Now we're accessing episodic memory, trying to find an event that matches this description, your head started moving, and trying to answer the question at the time of this event.
I have no idea.
Where was the red one when the green one appeared?
Most probably at the top, but maybe not.
Thank you.
You're welcome.
Good. So here you saw some of the new abilities that were aided by the use of the GSM. And of course, we believe that this whole theory of GSMs and the GSM as a platform can sort of support significantly many other extensions that we're going to see. So again, just to recap, we had imagining parts of situations in language, remembering and answering questions, verbalizing gradations of certainty, and a couple of other things. Now, what are the news in short? The system that you saw exhibits three novelties above the state of the art in conversational robots, as we're going to see in a later slide in more detail. It has a behavioral repertoire that's comparable in some terms and surpassing in other ways parts of the token test for children, which is actually a test that originally was designed for aphasics in the 60s. It was used for children later in 75. It's a human psychological test that assesses the capability of connecting language to the senses and to action. The third piece of news, apart from the fact that we have three novelties that we have, and that we have behaviors comparable to this children test for 3-year-old children, when it comes to the quantitative performance, the system is not infallible, but we have a pretty good performance. There are types of errors in trials that we ran that had a 10-step task. In all of them, we got 100% task completion, but there was a median of the need of one correction repeat of a statement per task. So there are errors, but the human, by repeating one statement, can actually go through them, and the errors are not catastrophic, as you can see. What's the main idea of the thesis? I will start with a sort of a comic depiction in order to try to introduce three main notions. So what do I mean by external reality? What do I mean by a situation model? And what do I mean by an embedded situation model? So imagine that a day comes where we build a second copy of Ripley, which this time is given the name Mrs. Ripley, and they cohabitate the table where Ripley lives. And this is a special day for Mrs. Ripley. It's her birthday. There is a separator between Mr. Ripley and Mrs. Ripley, and Mr. Ripley has bought a present for her. From where Mrs. Ripley is, she cannot actually see the present, so she doesn't know that there is a present, so she basically believes that Mr. Ripley has forgotten about her, and she's extremely unhappy, as any woman would be if she didn't have a present during her birthday. So this is pretty much a description of the situation as is. It's like a depiction of some more observer-independent, a little more objective reality, which is pretty much what I call external reality, and there are more specific definitions of this within the thesis. Now notice that normally in comics, there is this bubble over here that connects to the robot's head. And this bubble is supposed to depict the thoughts of the robot. So in this case, we have a depiction of some aspects of Ripley's situation model. This is what Ripley thinks about the current situation. These are his beliefs about the current situation, or at least a depiction of his beliefs. A partial depiction, actually, I would say. So these include a model of himself, a model of Mrs. Ripley, a model of the environment and relevant objects, and so on. Now notice that there is also a second bubble over here, which is basically what Mr. Ripley believes Mrs. Ripley believes about the situation. So we have a simple form of recursion, if you want. This is what I will call an embedded situation model, which is basically the estimated model of somebody's beliefs, which lies within the situation model of an agent. So we have these three different levels: external reality, the situation model itself, and the embedded situation model, which comes out of some form of simple mind reading when it comes to other agents, which contains, so this is things as they are, this is what we believe things are, and this is what we believe others believe things are. And a big part of this thesis relates with how you actually create representations of situation models and what processes can be used in order to update them on the basis of new information, and also what processes can be used in order to extract information from them, and so on. And how do you build agents around these representations? So let's give a layman's definition of grounded situation models. They're customizable model representations with standard processes that act as a theater in the head, containing descriptions of present, past, or imagined situations. Now, what are some requirements for GSMs? What are some basic things that they should exhibit? So the first requirement is probably multimodal connectivity. We would like these representations to be able to be fed by multiple modalities. If we have evidence about the situation through vision, they should be able to be fed by vision. If we have evidence about the situation through touch, they should be able to be fed by touch. If we also have evidence about the situation through some sort of a language statement, they should be able to be fed by that too. And on the other hand, they should be able to feed multiple modalities too. So they should be able to provide action parameters. They should be able to provide the right types of parameters for speech generation, and so on. The second requirement is that as we want these things to be able to interface with language, they should break down situations in the set of ontological types that is pretty much implied by the way that natural languages view situations. So there are many ways to describe external reality or parts of external reality. You can describe them in physical terms, in chemical terms. But when it comes to the way that natural languages view situations, they basically talk about situations as consisting of agents and objects and relations, agents having a physical and a mental part, everything breaking down to properties, and so on. And at the higher level, we also talk about histories that consist of situations and events. So these are the requirements for grounded situation models that led to the design that we're going to present in a very little while. Let's have a little deeper view to the bidirectionality requirement. So if we want to move from sensing to language and from language to sensory expectations, one should notice that for the case of sensory expectations, there is a very different level of specificity. So if I have something like a statement like imagine a red ball at the center, or imagine a laser pointer at the table, then basically I have much less information as compared to what I would have if I was actually seeing the laser pointer. So if I say that there is a laser pointer at the table, it might be here, it might be there, it might be a different type of laser pointer, it might be standing like this, it might be bigger, smaller. And I need to be able to carry all of this lack of specificity within my representation. And this is one big difference between sort of tokens that are instantiated within the situation model on the basis of language as compared to those that are instantiated on the basis of vision, for example. This is one of the main difficulties in designing such a system. So this was pretty much the general idea. You had a look at how things were, how things became. You had a look at the vision and the contributions of the thesis, the main salient idea, and some of the news. Let me now try to get in more detail. I will give a brief overview of the vision, the background, and the motivation, then talk about the computational model in more detail, then about the implementation architecture, the actual system, the evaluations, the future extensions, and the discussion. I will not get into many details about the postulated vision of this work. I'll just give you a definition, and you can get much more information about it in the thesis. So a situated conversational assistant is defined here as a system with sensing, acting, and speech synthesis and recognition abilities, which engages in physically situated natural language conversation with human partners and assists them in carrying out tasks. Ideally, we would like such systems to be truly cooperative, and I posit a continuum starting from dummy tools and going all the way to truly cooperative assistance. I give examples of this of systems along this continuum, and I talk about a set of axes along this continuum. And finally, I posit a set of prerequisites for attaining true cooperativity. The first of which is natural language interaction, and when it comes to Ripley's current capabilities, he's actually quite advanced as compared to other conversational robots in that terms. The other sort of prerequisites, Ripley cannot directly cover right now, but the GSM, as we will see in the future extension section, can provide a lot of hooks and a lot of levers towards getting there. So SCAs might be many different things in many different embodiments. It might be anything from theater lights to intelligent vacuum cleaners that are voice commanded or whatever you can imagine. So what are some sort of relevant notions from the literature? We can get inspiration or we can get useful information from three main areas. The first one is the area of situation models, which belongs traditionally in cognitive science. And over there, the sort of definition of a situation model is pretty much similar to what we have over here. It's a mental representation of a described or experienced situation in a real or imaginary world. The main difference that we have with what's going on over there is that over there they're talking about estimates of human situation models through behavioral experiments. Here we're talking about building situation models for robots. We have a much bigger level of specificity, and we don't really care about aligning totally with a human way. And also, in general, in this type of literature, they mainly talk about story understanding and the effects of understanding stories within the situation model. While in our case, we also give explicit sort of attention to how situation models are updated through sensor information. Another two areas that are sort of relevant is the area of symbol grounding in general. So whenever you have a closed system of symbols, in order to try to get a definition of meaning for them symbols, you cannot stay within the system. You need some sort of an external meaning space in order to get a non-circular definition. And normally this meaning space is some form of a description of external reality. And there is all of this literature that deals with symbol grounding and language grounding. And Deb is one of the main contributors in this area too. Finally, there is situated language, which belongs to sort of developmental linguistics. And there we're talking about the sort of language that children develop during the first years of their life, which has a difference from sort of more advanced language through the fact that it's basically language about the concrete here and now. So before you extend to things that are outside of your spatio-temporal horizon and which are abstract, you start talking about very concrete and tangible things that are accessible to you. So how do we motivate GSMs? Again, very quickly, you heard about the main motivation, building cooperative situated conversational assistants, very practical as a motivation. Other motivations, trying to answer some questions in cognitive architecture. So there are vision systems, there are motor control systems, there are sort of speech synthesis and recognition systems. All of them have different representations in their inputs and outputs. How can we get them together? And here we have a proposal for doing that. There are other proposals, of course. Then there is the area of, again, situation models, if you want. How can we get to provide a computational model of a grounded situation model that's similar to the ones that humans have? And then there is also, again, the sort of semantics or language grounding motivation. And the question is, what can we learn about sort of language grounding through the mediation of situation models? So enough with motivation. Let me go to the actual core of the proposal, the computational model that's being proposed and that was actually implemented too. And this is a computational model that can be customized for different systems. First of all, the representational hierarchy. As we said, there are two desiderata, the folk ontology of language and multimodal connectivity. The main type is a situation type. Each situation breaks down to a set of descriptions of agents and a set of descriptions of agent relations. Each set of description of agents breaks down to three parts, to a physical part, a mental, and the interface, as we call it. The physical part is pretty much a description of the body of the agent. The mental part is the embedded GSM plus a couple of other things. The description of the body of the agent breaks down to a set of properties like position, shape, color. And each of these properties is represented through three parallel layers of descriptions, the stochastic, the continuous, and the categorical layer. So we're actually sort of replicating the folk ontology through this hierarchy, and through this lower part, through these three parallel layers, as you're going to see, we're trying to solve the multimodal connectivity and bidirectionality requirement. So the question then simply arises, why should there be three layers? The short answer is simple. So we choose representations on the basis of whether they're suitable or not for what we want to do with them. And let's get an example. Consider an object, a ball, which is part of a situation, and say that we want to represent its position, one of its properties. So imagine that we have three tasks at hand. Seeing a ball and noticing its position under uncertainty, so getting sensor information. Needing to grasp the ball, the second task, or hearing that the ball is at the center. Then the question is, what is a matching representation of the position for each of these three cases? The answer that we propose is that for the first case, for sort of gathering information from the senses, a matching representation is what we call a stochastic layer representation, which is basically a multidimensional continuous distribution. A matching representation for the second sort of requirement for driving action parameters, in that case, we cannot afford multiple values. We have to actually get the gripper to go to a specific place. So we basically just choose a single value, and we get a multidimensional single value, not a distribution anymore, what we call the continuous layer. And for the third requirement, which is being able to interpret a linguistic statement, we cannot be in the continuous sort of space anymore. We need to go to some sort of a discrete space, and we actually build a distribution on different symbols, on different categories. So, for example, if we hear that the ball is most probably at the center, then we're going to create a distribution on verbal categories that deal with position. There's going to be one category that's at the center, another that's at the left, another that's at the right, at the top, at the bottom. And we're going to give different probability values to these categories on the basis of the statement. So this is sort of the third layer of representations, the categorical layer. Let's get a wider view of the three layers and see how they connect with each other. So traditionally, within sort of the field of representation, there is one sort of a main camp that deals mainly with logical statements, with crisp symbolic logic, and another camp that deals much more with sort of stochastic signals. So this is where people from signal processing normally are, and this is where people that have a more logical background and computer science background normally are. So what we're trying to do over here is to create this sort of four, in reality, layers. The fourth one is not explicitly represented, but it's actually being driven through language. Across the two sort of